Hi ladies, Mrs. Blaufuss here again. This is lesson 2.5 for Algebra 2 with Trig, and it's about modeling using direct variation. So we looked at graphs already, and we're specifically looking at graphing linear equations. And we looked at a few different forms with that, but now we're going to look at specifically direct variation, which a lot of our graphs do already very directly, but a direct variation graph has a specific feature where it has a zero y-intercept. So it always, the graph for a direct variation model always intersects at the point of origin, which is 0, 0. So a couple of vocab terms, you've got direct variation and constant variation. For direct variation, we're going to write our direct variation model in the form y equals a times x. And this describes change in y values that vary directly with change in x values, hence the name direct variation. And with our direct variation model, y equals a times x, our constant a, so our constant of variation is a, but a cannot equal 0. On your guided note sheets, you'll see this key concept, which is just the definitions that we discussed on the previous slide. But the equation y, I should say y equals ax represents direct variation between x and y is said to vary directly with x. So it's proportionately. So every time x increases, y increases by a proportional amount, and that proportion is a. So here, instead of saying our slope-intercept form, we say y equals mx plus b. We don't have a b here because our y-intercept is always at the point of origin, which is 0, 0. So our y-intercept is 0. And our slope, or our rate of change, instead of calling our slope, we're going to call it our constant of variation. So y equals mx plus b becomes y equals a times x. And our b is 0, so plus 0. Okay, so for example, this first one asks us to write and graph a direct variation equation. So first, it gives us the solution, -3, 2. So we're going to go through this point, -3, 2. And with our direct variation model, we always start at 0, 0. But when it gives us a point like this, when it gives us a solution, and we have the formula for our direct variation model, y equals a times x, we look at the y value, which is 2. We can say 2 equals whatever the constant of variation is times -3. And then we can solve for that constant of variation, or solve for a. So our a equals -2 thirds. So when we graph this, we have our point of origin here, 0, 0, and we go, our rise is -2, and we go to the right, our run 3. And so here's what our graph looks like. And if we were to extend it, we would see, oops, we would see that it also goes through that point of our solution. So on your own, try this exercise. It says write and graph a direct variation equation that has an ordered pair of 4, 2. Oh, that should say 4, -2. And on your guided note sheet, it has a box. There was just error in, I think, the error in the font. So try this one on your own, pause your video if you need to, and then unpause for the solution. So we have the direct variation equation model, y equals a times x, and we have a y and we have an x. So we can say -2 equals a times 4, and then solve for a, and a equals -1/2. So that's our constant of variation. Y equals -1/2 x is our new model. Y equals a times x. And we know that we start at 0, 0, and our constant variation is -1/2, so we'll go down 1 and over 2. And then that's our graph. Oops, it's pretty thick. Let's change that. And then we also see that it goes through the point 4, -2, which is our solution. So now using direct variation models for word problems, or more complex story problems. In this example, and on your guided note sheets, it's a little fuzzy, but you can follow along with the diagram on your screen. It says hailstones from when strong updrafts support ice particles high in clouds where water droplets freeze onto the particles. The diagram shows the hailstone at 2 different times during its formation. So here's at 20 minutes, and here is at 12 minutes. And we know the diameter is 0.75 inches at 20 minutes, or at 12 minutes. And it's asking us to first write a model that gives the hailstone's diameter in inches after t minutes, if you assume the diameter varies directly with the time. So diameter varies directly with the time. So our diameter is our y, and our time is our x. So we can assume, since it tells us to assume that it varies directly, for part A, we are going to say the diameter varies directly. So A, our constant of variation, times time. We have a diameter for 12 minutes. So we can say 0.75 is the diameter for A times 12. And then we need to solve for A. So we'll divide both sides by 12. And 0.75 divided by 12 is 0.0625. So that is our constant of variation. So to write a model for this, we can say D equals 0.0625T. Now it says use your equation to predict the diameter of a hailstone after 20 minutes. So we don't know the diameter, but we know the constant of variation, and we know the time. So if we multiply a constant variation by 20 minutes, we get a diameter of 1.25 inches. In the next example, it says, according to Hooke's law, the force that is needed to stretch a spring varies directly with the amount of spring attached. So the force varies directly with the amount of spring that is stretched. So if 64 pounds of force stretches a spring a distance of 8 inches, we can say the force varies directly with the amount of the force needed to stretch a spring varies directly with the amount of spring that is stretched, which it says the amount of string that is stretched it gives us as distance d. Force equals F equals A times D. Write an equation that relates F and D. So force varies directly with the spring that's stretched, so how far it's stretched. Predict the amount of force that is needed to stretch the spring to 14 inches. So we first need to, in part A, we first need to find our A. So it says if 64 pounds of force stretches the spring 8 inches. We can solve for A, and we get A equals 64 divided by 8, where A is 8. So in the second one, predict the amount of force that is needed to stretch the spring 14 inches. The force equals our constant of variation times 14 inches. And then we can solve for F, and we get 112 pounds. Now, with a direct variation, we say y equals ax, but it doesn't really matter which one you put in for a and which one you put in, or which one you put in for x and which one you put in for y. For example, if I would have written my equation d equals a times f, I would get 8 in the top section. I would have gotten 8 equals a times 64, and I would have gotten an a of 1/8. And then when I found the force needed for 14 inches, I would have said that 14 equals 1/8 F. And then I would have multiplied both sides by 8, and I would have got F equals 112 pounds. So as long as you're consistent with the x values and the y values you're using, you'll get the same answer for your solution. Okay, this next example you should do on your own, and you can pause the video as you're working. You should use one of the models, and it doesn't matter which one as long as you're consistent with the x's and y's that you use. It says in example 3, suppose that the force being applied to the spring is 92 pounds. How far is the spring going to be stretched? So pause the video and work this out on your own. So you would have either used the model F equals A times D, or D equals A times f. And either way, when you do that, you should get the distance equals 11.5 inches. So if you use the first model, your force is 92 pounds. Just rewrite this. So if you use the first model, your force was 92 pounds, and that equals our A, which we said was 8 times C. And if you use the second one, you got D equals 1/8 times force. Oh, which our force is 92. So 92 divided by 8 is 11.5. And then if you solve for D here, you would have divided by 8 on both sides, and 92 by 8 divided by 8 is 11.5 inches. Make sure you use your units. Okay, so this next one, the table below gives a cell phone bills showing the total monthly cost and the number of minutes, and use that month. Tell whether the total cost and total number of minutes show direct variation. If so, write an equation that relates the quantities. So for this one, you'll have to look at your y equals ax and solve for a to see if it's consistent with each pair. So for the first one, we could say that our total cost, I'm going to say that our total cost varies directly, or I'm going to try to prove that our total cost varies directly with the minutes used. So our total cost is 35, varies directly with the minutes used. And I'll solve for A. And I'll do the same thing for the second one. 45 equals 8 times 129. And I'll do it again for the third one. 80 equals A times 229. And then I'll do it again for 15. And for $30. A times 86. So if I solve for my A's, and to do that, we'll isolate the variable. So in this first one, we'll divide both sides by 35, and we get A equals 0.35. For the second one, 45 divided by 129, and you can do this in your calculator to check. I get A equals 0.349, which is pretty close to 0.35. And then the third one, if I solve for A, 80 divided by 229, I get A equals 0.349 again. For the first one, for the fourth one, if I solve for A, 15 divided by 44, I get 0.341, which is still pretty close. It's about a penny off per minute. And then for the last one, 30 equals 86A. Divide by 86, I get A equals 0.349. So all of these 0.35, 0.341, all of these A's are pretty close, within 1/1000th, or for this one, just 1/100th off. So I'm going to say yes. This varies directly, where C equals A times M, where C is the cost and M is the minutes. So for my equation, I can say that the cost varies directly with the number of minutes used, with a constant variation of 0.35. And then lastly, try this one on your own. So use the same model we did here. Here's your pairs of x's and y's. pause the video and then unpause for the solution. So we have, remember, the form y equals ax. And you're looking for a constant variation that is the same for all of these. So if you do this on your own, the first one you want to compare -2 and 1, where -2 is our y, equals a times -1. And you'll do that for all of them. So 2 is a times 1, and so on, all the way up to 14 equals a times 7. And if you solve all of those for a, you get a equals 2. For every one of them, you should get a equals 2. So your expression relating x and y is y varies directly with x with a constant variation of 2. So y equals 2x. So as always, please jot down any notes, any questions that you had during this note session, and bring those to class with you next time I see you. Thank you.